Chapter 8, the daily growth rate. This is an interesting statistic. How do these exponential growth rates correspond to a daily growth rate? If we have a given model, in this case, the exponential growth rate is 0.135, what does that mean on a daily basis? Well, there's a very simple formula. D equals e to the r sub e minus 1. And if you want to go backwards, RE is natural log of 1 plus d. So this isn't just for virus spread. This is for exponential models. And this could be, if time was in years, this would be a yearly growth rate. You can apply it to any time period. So in this case, we have this model, 15e to the 0.135t. R sub e is 0.135. And we can get the daily growth rate is e to the 0.135 minus 1 equals. Okay, let's go ahead and calculate that. And let's see. And we get 0.145, which is 14.5%. It's usually a little bit more than this. This would underestimate the daily growth rate if you're interested in what that number means. This is actually the continuously compounded growth rate. If you study compound interest, if that was 13.5% annual, you could compound 13.5% compounded annually, then semi-annually, and then quarterly, then monthly, daily, by the hour, by the minute, by the second, and it would actually approach 14.5% if you take the limit as a number of compound periods shrink to infinity. So this will always understate that. Let's turn this problem around. Let's suppose we know the daily growth rate. This is something you could look on a table, and if you're testing thoroughly in a population, you could tell how fast something's progressing daily. If you were running a school, if you were a superintendent for a school, for instance, you might know this based on how many absenteeisms you had. Well, RE is just simply going to be natural log of 1 plus this, natural log of 1 plus 0.20, and we can do that. And we get 0.182. And again, that's the R sub e, and of course the daily growth rate is a little bit in excess of that because of compounding. And let's suppose I0 is 50. Well, now we can build our model. I of t is equal to 50 e to the 0.182t. So everything we're applying to viruses applies to any other form of exponential growth, whether or not it's population. Radioactive decay is the same math. It's just that we have radioactive isotope decaying. So this is good math apart from virus spread. So that's it for Chapter 8.